everyone, welcome back to discussion. In this discussion, which is discussion 7, we're first going to be doing a problem on gradient descent, and following that, we're going to be doing a problem on ROC curves. Okay, and so for problem 1, I'm going to start by doing some linear algebra review that is relevant for the question, and then afterwards, I'll do a quick overview of what gradient descent is, and then we'll dive straight into the problem. And so for linear algebra review, the first thing I wanted to do is kind of identify 3 kinds of feature matrices situations that we might be in and what each of those situations implicate. And so given a matrix X, such as a feature matrix that we often see in machine learning, the shape of this matrix dictates the number of possible solutions to a linear system, like x theta equals y. And that becomes really important later on. And so the kind of 3 scenarios of like matrix shapes you can have is first, when the number of rows, which we denote as n, is equivalent to the number of columns, which we denote as d. And so here you have a square matrix. The second possibility is when n is greater than d. And so here we have the number of rows, which is represented by n, is greater than the number of columns, which is represented by d. And the last scenario you can find yourself in is when n is less than d. In this case, the number of rows, which is n, is less than the number of columns, d. And so what is the significance of all of this? Well, first I want to give you a key idea. And so remember that x, we can think of it as a feature matrix when we're looking at matrices within the context of machine learning. And a key idea here is you can think of each column as a feature. So if this was like your entire, if this was your entire data set, right, you can think of each column, so we have d columns, you can think of each column as like your feature. For example, this is data on age, this is data on year, this is data on major, etc., etc. And you can think of each row as a specific data point. And so, for example, if our columns D were age, year, and major, then one specific row could be a very specific data point, like you're 20 years old, you're in your 3rd year at Berkeley, and your major is CS. Okay. And so for these kinds of feature matrices, you can essentially think of it as we have n data points and d features. N data points, right? Because we have n rows, each row representing a data point, and we have d features, each feature being like a feature of the data we collect, like the age or the year. And this creates our n times d feature matrix that we've been working on throughout this course. And so some quick like significance behind like why do we care about these dimensions. Here is a chart that kind of goes over it all. But before we do that, I want to clarify some quick matrix terminology. So when we say, oh, I'm looking for the rank of a matrix, this is review hopefully from Math 54 or an equivalent linear algebra course. So when we talk about the rank of a matrix, we're talking about the number of linearly independent columns / rows. It doesn't matter. The number of linear independent columns in a matrix is always equal to the number of linear independent rows in that matrix. So that's what the rank means. When we say a matrix is full rank, that means the rank of the matrix is the highest it can be given the limitations of the matrix. AKA the number of linear independent columns or rows is like the maximum it can be given we have like an n times d matrix. And so we really have a lot of scenarios here because depending on whether there are more rows or more columns, the maximum rank like depends on the number that is smaller. And to better illustrate that, let me show you here like what it means when a matrix is like full rank. And so note in this chart that we assume every feature matrix X is full rank. AKA we have the maximum number of linear independent columns or rows possible given the limitations of the matrix. So um, either there's more rows or more columns, and basically whichever dimension has less rows or less columns determines the full rank. And so let's first look at the scenario where n equals d. If n equals d, our full, like the rank of our matrix, if its full rank is either n or d. Since they're equivalent, it doesn't matter. And in a square matrix, when we're solving a system of linear equations, such as x theta equals y, and theta is kind of the parameter weights that we're trying to find, the number of solutions is just 1. And how come? Since n is equal to d, when you create a system of equations with x theta, the number of resulting equations is equal to the number of unknown variables. You can think of this matrix, right? When you multiply this matrix by like our theta values, like theta 1, theta 2, whatever, then all the way to get y, which is our output. Basically, the number of equations that you will end up creating will be exactly the same as the number of unknown variables. So the number of resulting equations created with the variables x1 through xn is equivalent to the number of unknown variables, which are the thetas. And so this gives us one guaranteed unique solution. Now let's look at the second case where n is greater than d. When n is greater than d, we have more data points, right? More rows than we have columns, than we have features. And so our full rank is, oh, sorry, I think I actually wrote this backwards. That's my bad. Yeah, big oops. Guys, I'm so sorry. I like legit made the worst mistake ever. So when n is greater than d, there are more rows than columns, and the full rank is the highest value, the highest rank. It can be given the limitations of our matrix. And since there are less d's, less columns than rows, our full rank is always the smallest number. So it should be d. And so when n is greater than d, our full rank is d. And our system of equations also only has 0 or 1 solution. Why is that the case? Well, when n is greater than d, there are more data points than unknown variables, which are the weights. And you can kind of think about it as having 3 data points, for example, but you're trying to fit it to a 2-parameter model, like a line, right? Like if you have, it's like you have more data points than you have like weights to kind of like create the model. And so for a very specific case, like for example, having 3 points for a 2-parameter model like a line, I mean, there is a possibility that all 3 of your points happen to end up on line, in which case there might be one solution. But there's also the case where you can't draw a perfect line for those 3 points. And so you're not guaranteed a solution when the dimension of n, the number of rows, is greater than d, the number of columns. And your full rank for this matrix will be d, basically the smaller number. And lastly, the opposite. When we have a really wide matrix, when we have n is less than d, right? So the number of rows, aka the number of data points, is less than the number of features. Then for our rank, our full rank is the smaller number, which is n, and the number of solutions here is actually infinitely many. And the logic is kind of similar as previously, but backwards. And so when n is less than d, there are less data points than unknown variables or weights. So you can think of it, because like n is like the number of data points, right? So you can think of it as having 2 data points for a 3-parameter model. A 3-parameter model might be like a quadratic equation where it's like ax squared plus bx plus c, and a, b, and c are your weights. There's like, if you only have 2 points and you're trying to fit a quadratic like a parabola, right? There's like, you can fit so many parabolas through just 2 points. And so there are basically, you're kind of guaranteed infinitely many solutions when your matrix is full rank. Remember, in this chart, we assume our feature matrix X is full rank, aka this means you have n. Your rank is n, so you basically have n linearly independent rows and n linearly independent columns, and n is less than d. So when this case happens, we have infinitely many solutions. Okay, and the reason why I went over this whole thing about rank and stuff is like you'll basically see later. But again, intuitively speaking, rank of a matrix is just the number of linearly independent columns, and that's also equivalent to the number of linearly independent rows, because the row rank is equivalent to the column rank in any matrix. And for a full rank matrix, which is what we're talking about here, the rank of the matrix is basically the rank of the dimension that is smaller. And so when n is greater than d, a full rank matrix has rank d. When n is less than d, a full rank matrix has rank n. Okay, lovely. Now, continuing on with linear algebra review, recall what the kernel or null space is. So for some matrix A that is of dimensions m times n, so A is a matrix of n times n dimensions, the kernel space of A, it is a subspace that represents all input vectors x such that A times x is equal to 0. Basically, the kernel space is a subspace that contains a set of vectors that map, basically the matrix A maps all of these vectors in the kernel space to the 0 vector. And so if x equals 0, which is also a trivial solution because any matrix A times 0, well, it's going to be equal to 0, right? So if x equal to 0 is the only solution, then the columns of A are linearly independent. And this is just a rule in linear algebra. If you forgot or are still confused, I encourage you to look further into linear independence and what that means. But this is essentially a fact. When x equal to 0 is the only solution to ax equal to 0, then the columns of A are linearly independent. On the other hand, if there exists x such that x is not equal to 0, that still satisfies A of x equal to 0, then the columns of A are linearly dependent. In other words, the dimensions of the kernel space is greater than or equal to 1, because before the dimensions, if all the columns of A are linearly independent, then the only answer to ax equal to 0 would be x equal to 0, and that has dimension 0. And so if there exists a vector x such that it's not equal to 0 and still satisfies the fact that this non-zero vector gets mapped to the 0 vector, then the columns of A are linearly dependent and the dimension of the kernel space is greater than or equal to 1. And this idea of kernel space we're going to use a lot in our first question in this discussion. And another terminology reminder is the column space is a set of all linear combinations of column vectors, and they basically represent the span of the columns. Okay. Lastly, I want to quickly go over the general idea of gradient descent. Hopefully you're familiar with this through lecture, but if not, the general idea is we basically want to approximate or find weights, theta or w, depending on the variable, that would minimize our loss. And this is especially helpful when we cannot find a closed form solution. So gradient descent is basically an iterative optimization algorithm. It has an initial estimate of weights, such as we notate it as theta 0 or w 0, and then we refine it through a following process. And the process is basically we get the old weights and we subtract it by some learning rate times the loss surface. So essentially we're trying to minimize our loss surface, and to be able to do so, we start with some initial weights. Oftentimes we just initialize all our weights that we're trying to kind of tune. We just initialize all our weights, equivalent we're just initialize all our parameters to 0. And afterwards, we calculate the gradient of the loss function at these weights. So remember, calculating the gradient, L, it gives us the direction of biggest increase on the loss surface. So if we want to try to go to the minimum of our loss, right? Because we're trying to minimize the loss, we want to go in the opposite direction of the gradient L. Hence, we have this negative gradient L, which basically says we want to go the opposite direction of greatest increase to try to get to the minimum. And so this is what the gradient of L is. And we also have a learning rate, which can help us, basically we can control this parameter, and it helps us adjust or control how large of a step we take. So gradient L gives us direction. You can think of the learning rate as kind of giving us the magnitude of how large of a step we should take. And then, so we start with these old weights, and then we end up with new weights after a gradient descent step. And so again, the purpose of gradient descent, in the past, we've been minimizing our loss functions by basically calculating argmin of some function. And that's nice when it works, but there are a lot of functions where we cannot just calculate like, or we can't find a closed form solution, or it's not really easy to like calculate a formula for the minimize, like the minimum the weights that would minimize the loss. And so gradient descent is basically an iterative algorithm that helps us approximate the minimum. And it does a pretty good job oftentimes, as we'll see. Okay, and so this was all kind of review / context for question 1. Now let's actually dive into discussion 7, problem 1. So this problem is called gradient descent on squared loss, and it says, consider a regression problem with design matrix X, it's like our feature matrix, of dimensions n times d, corresponding labels Y, which is of the real numbers, and parameter vector theta. And our loss function is basically just the actual label minus our predictions squared. It says assume that d is greater than n. So the system is over parameterized and x is full rank. Again, full rank, as a reminder, it just means that it takes the maximum rank possible. And since we're in the case where, let's see, what case are we in again? D is greater than n, aka n is less than d, right? So we're basically in the case where we have a super wide matrix where d is greater than n, and our full rank is thus the smaller number, which is n, and we should kind of have in our heads that this like equation has infinitely many solutions because of reasons we just talked about. Okay, and so it's over parameterized. X is full rank, and gradient descent generates a sequence of points, theta k being our parameters, according to this update rule, which we also just talked about, right? We have the initial parameters, and then we calculate the gradient of the loss function at that point to get the area of steepest increase, and then we subtract it to get the areas to like decrease it. And then we basically have a learning rate that controls our step size. And so we assume that theta 0, our initialization of our parameters, is 0, and that the learning rate is greater than or equal to, the learning rate is chosen so that the gradient descent converges to a minimizer of the loss function. So we're basically told that gradient descent converges, and it converges specifically to a minimizer of the loss function. And sorry, this theta k is greater than or equal to 0 is basically saying like, it's basically saying k equals 0, k equals 1, k equals 2. So every time we take a step, there might be a different learning rate. And it's basically chosen such that it converges. Okay, and so part A says, show that there exists infinitely many thetas such that x theta equal to y. So infinitely many solutions. We kind of already know this by our chart above, because we know that, oh, like we're in this scenario, right, where there's more features in our data points, our model is over parameterized, so like that makes sense that it should be infinitely many solutions. But now it says, please show this. And so let's start by first showing that theta actually exists. Like there is a solution first to x theta equal to y. So first, we know that a solution, let's call it theta star, exists if our output y is in the column space of x. And I just defined column space above, but if you forgot, here's an easier way to think about it. Basically, we want to show that y can be written as a linear combination of the columns in x. And basically, how we can do this is we can essentially show that, or show it by saying, first, we know that our matrix is full row rank. Or, yeah, we know it's full rank by the problem. And we know it's full row rank because D is greater than N. So there's less rows than columns. So we know that it's actually like full row rank specifically. And basically, our full rank is equal to N, the smaller number. And because row rank is equal to column rank, we also know like basically the number of linearly independent rows is equal to the number of linearly independent columns. And since it's full row rank, the number of linearly independent rows is n. And so because of full rank, and remember what full rank means, is full rank is the number of linearly independent rows/columns. And since there are n linearly independent rows, there's also n linearly independent columns. And so all of this was to say that we know there are n linear independent columns. Again, how we know it's n linearly independent columns is because the number of linearly independent columns is equal to the number of linearly independent rows, and the number of linearly independent rows is equal to the row rank. And we know we have a full row rank because n is less than or d, right? So our rank is determined by the number of rows, and that's n. And so we know there are n linearly independent rows, therefore there's n linearly independent columns. Hopefully that kind of made sense. And because there are n linearly independent columns, then basically the columns of our matrix must span all of Rn space. Because there are n linearly independent columns, they can basically take on every dimension of Rn. So they must span all of Rn space. The column space must span all of Rn space, which means the solution theta star definitely exists. Again, it's because X can be represented as n linearly independent columns. We know this because we were told that X is full rank and D is greater than N, aka N is less than D. So we have n linearly independent columns, which means that the matrix X must span all of Rn space. And X spanning Rn space is good because this means that y is in the column space of X because y, the vector y, is in Rn. All this convoluted, this was a whole convoluted way of saying, hey, we have our feature matrix X, we can have theta weights such that we can write the columns of X as a linear combination and it will span all of Rn space. And because y is one vector in Rn, then this feature matrix must be able to, with multiplied by this theta, must be able to reach y because y takes up one vector in Rn space and we can reach all of Rn space through this. Okay, so the convoluted way of saying, yes, there must exist some theta such that x theta equal to y exists because we can map the theta to any vector in Rn space and y is in Rn space. Now, we want to say, okay, well, not only does there exist one solution, but like a solution exists, but also that it's not just a solution, but it's infinitely many solutions. So that's kind of the second part we want to show. And we can say, hey, in fact, infinitely many solutions exist. And then why is that? Um, here's the reason why. Because there are more columns than rows, right? Because again, D is greater than N. So there's more columns, D, than there are rows, N. That must mean that some columns in X must be linear dependent. And don't confuse this with our conclusion earlier. Our conclusion earlier was that there are n linearly independent columns because there are n linearly independent rows, and due to full rank, and our row rank is equivalent to the column rank. And because there's full row rank and it's equal to n, which is equal to our column rank, if there's n linearly independent rows, it's equivalent to the number of linearly independent columns, which is also n. But now we're saying, although there are n linearly independent columns, how many columns are there actually? There are actually d columns, right? There's actually more columns than n. N is the number of rows, and there's d columns, so there are more columns than rows. And so some of these columns must be linearly dependent, right? Because there are like way more columns than there are rows. So like you have way more columns than you need to span all of Rn space. You have d columns, in fact. And so therefore, some columns in X must be linearly dependent. And recall, if some columns in X are linearly dependent, there must exist, so there must exist some vector z not equal to 0 such that xz equal to 0. And this is the property that we saw earlier. So the reminder is if all rows are linearly independent, or all columns, sorry, not all rows. If all columns are linearly independent, then xz equals to 0 only when z is equal to 0. However, now we know that the columns in X must have some linear dependency for some of the columns, just because there's a lot of columns compared to the number of rows needed to basically take up the span of Rn space. Then there must also be some vector z that's not equal to 0 that still manages to map to 0. And this is our whole kind of null space idea, right? If x equals 0 is the only vector that can map this input to 0, then we know the columns of A are linearly independent, and vice versa, actually. And also, if the columns of A are linearly dependent, then there exists some vector such that it's not equal to 0 and still maps to 0. So I suppose a better way to describe this actually is this is really an if and only if statement. Yeah, it goes both ways. Cool. And so back to our question, basically, we've just shown that in our feature matrix, there are more columns than rows. So some columns next must be linear dependent. And so there exists some vector z such that xz is equal to 0, but z itself is not the trivial 0 vector. And why is this like helpful? Basically, another way to say this actually before I go on. So another way to say this is that the kernel, remember the kernel / null space, or let's say the dimensions of the kernel space actually, dimensions of the kernel space is greater than or equal to 1. And we also talked about this in our earlier notes. And this is where kernel space encompasses a set of all vectors in the input space that maps 0. Okay, and so knowing this, we can let a new theta prime. So remember, our solution is theta star, right? But we want to say there's actually infinitely many solutions, and theta star isn't the only solution. So we let theta hat be theta star plus some random some random multiplier alpha, and we multiply it by z, where z is some vector in our kernel space, right? Because it maps to 0, but z is not equal to 0 itself. And we know that, or we can say that if we have this holds, then x theta prime is really equal to x theta star plus alpha z. And this is equivalent to x theta star plus alpha x theta z. So we can distribute this. And we know that theta z, or actually, wait, did I write something wrong? Ooh, my bad. This this should be alpha xc. There we go. Right. Okay. So we have x theta star plus alpha xc because we multiplied here, and xz, it basically is, it maps to the 0 vector, right? So this whole thing is essentially the 0 vector, and what that means is this whole thing is equal to x theta star. And so we've literally just shown that if we create a new theta prime that's theta star, and we add basically a vector in our kernel space, a vector that maps to 0 to it, then when we calculate x theta prime, we can like write all out, and x theta prime ends up just equaling x theta star. And so what we've just shown is that for infinitely many scalars alpha, right, because we can literally turn alpha into anything, it doesn't matter. For infinitely many scalars, alpha is in the real numbers. We have theta prime equal to theta star plus alpha z, and this is also a solution. So there must be infinitely many solutions. Great. And if a lot of this linear algebra like went over your head, like it's totally chill, the main kind of purpose of this question, I suppose, was basically to tell you that for an over parameterized model, so our feature matrix has a lot more parameters, or it has a lot more like, yeah, you can say it basically has a lot more features, which means it has a lot more parameters to tune than it does have data points. So like there's a lot more d than there is n number of data points, and so we basically can over parameterize. And so in this very specific case, we actually have infinitely many solutions. Okay, so we have infinitely many, I guess, equivalently valid solutions that we can use to parameterize our model. And so in terms of like how is this significant to anything, like think about gradient descent, right? Gradient descent is trying to find some minimizer, right? Some theta, some optimal theta that will end up basically some parameters theta that will minimize our loss. But we just said for this very specific case, when there's more columns, when there's more d than there are data, than there are n, like legit there are infinitely many solutions. So like Loki, what is gradient descent doing? Like which solution is it actually getting? And that's actually the interesting part of this question. So let's move on to B. And basically in part B, we say, show that the gradient descent limit. So as we take more and more iterations, right, we like run the iterative algorithm multiple times until we like go to like theta infinity. Like basically the minimizer, the thetas that minimize our loss is actually the minimum Euclidean norm solution to x equal to y. So earlier we showed in this specific problem there's many thetas that could take, right? Because you can add any kernel space vector to a theta and it'll create another solution because they're literally equivalent. But we're saying that gradient descent actually reaches one specific solution, the minimum Euclidean norm solution. And for context, what is minimum Euclidean norm? It's basically the vector with the smallest possible magnitude. Like that's literally what this means. It's like low-key overcomplicated words for a very simple concept. So minimum Euclidean norm just means the vector with the smallest possible length or magnitude. Okay, and so first, to show that the gradient descent limit is the minimum Euclidean norm solution, let's actually, you know what, I'm gonna troll. I'm actually going to duplicate this page. Can I duplicate this? How do I duplicate this page? Current template. Okay, I'm gonna duplicate this page and then I'm just gonna like casually like remove this so we have more space. Actually, can I make this white? Oh, yo, this is low-key. This is like low-key pretty cool. But I can't like erase this because otherwise this text will appear back. Okay, slay. You can kind of still see the. Actually, no, it's fine. No one cares. Okay, so let's show that the gradient descent limit is the minimum Euclidean norm. It's the smallest vector, smallest possible like magnitude vector as a solution. Writing out the gradient descent limit, we can do theta k plus 1 is equal to theta k minus alpha k times the gradient of the loss, and this is just the definition of gradient descent. And I'm gonna first start by writing out the loss and multiplying it and then plugging it into this equation. Okay, and so the loss, theta k, if you look at the problem, our loss is given as this guy, as this guy right here. And so we have the loss is equal to y minus x theta k squared, which is equivalent to y minus x theta transpose y minus x theta. And when you take the gradient of this, the gradient of L theta k, you could just write this all out and like, you know, multiply it, solve it, take the gradient of each one. But this one is low-key kind of worth memorizing in my opinion. It's kind of almost like normal, like instead of taking like vector calculus, just think of it as normal calculus where you move the 2 into the front. So the gradient is 2y minus x theta k times, by the chain rule, the inside one, because we're taking with respect to theta k. So you would think that it's negative x, right? But it's not quite. And the reason is because the dimensions don't match. And so to make sure the dimensions match, what ends up happening is the negative sign stays, it goes up here. And instead of having x in the back, we actually end up moving x to the middle term and then transposing it. And this basically ensures that the dimensions match. If you actually want to multiply this all completely out to get this, we actually did so in one of the previous discussions. So definitely look at that. But to save your time, I recommend low-key just memorizing, like just remembering that, oh, when I take the gradient of this L2 norm, basically you take the gradient normally, except when you multiply again by negative x, instead of multiplying by negative x, you multiply it by negative x transpose, you move the x transpose to the middle. Okay, but yeah, you can solve it if you don't believe me. And so after we've done this, I'm going to plug in this loss to our, or this, the gradient of the loss to our original gradient descent problem. So it's theta k plus 1 is equal to theta k minus, or now because of the double negative, it's minus minus, right? So it's plus alpha k times 2x transpose y minus x theta k. And now, before we show that the gradient descent limit is the minimum Euclidean norm, I'm actually going to show you something pretty cool, which is I'm actually going to show that every update, right, every update from theta k to theta k plus 1, and theta k plus 1 to theta k plus 2, every update is actually perpendicular to the kernel space. In other words, every update is perpendicular to KER, kernel space. That's a perpendicular sign. So every update actually falls into this subspace. I hope you can read that. That says kernel, by the way. Oh. Okay. And I guess what's interesting about showing this is basically showing that the gradient descent limit is basically falls into the perpendicular space of the kernel space. And so let me just write that for note. So we can then show that the gradient descent limit is also perpendicular to kernel space. So, which I guess is better written as is also in the kernel space, but perpendicular to the kernel space. Like it's in the perpendicular space to the kernel space. And two quick notes right over here is recall that two vectors are perpendicular to each other if their dot product is 0. And also recall that the dot product A dot product B is equivalent to A transpose B. Okay, wonderful. Hopefully that helps us. And so what I'm going to do is I'm going to first show, like, we want to show that every update is perpendicular to the kernel space, so it falls into this. And specifically, we want to show that our gradient descent limit actually ends up being in the space perpendicular to the kernel space. And that's going to be really cool for a very specific reason, because it can help us show that the minimum Euclidean norm solution, aka the vector with smallest possible length, is actually the final solution that we get to x theta equal to y, even though there's infinitely many thetas that could be here. And to do that, we're going to do some nice induction. And so hopefully you remember this from CS70. If not, it's totally fine. So let's start with the base case. So my base case, we have, like, we start with theta 0, right? Like, our initial parameter rates are 0 because we're given in the problem that we initialize them to 0. And when we initialize them to 0, we know that this theta 0 falls into the perpendicular, the space perpendicular to the kernel space. And it's interesting. Zero, or the zero vector, falls into the kernel space itself, right? Because ax equals to zero, so a times any matrix times a zero vector is equal to another zero vector. But interestingly, this zero vector also falls into the space perpendicular to the kernel space. And the reason is dot product anything with zero, and it's equal to zero. So two vectors are perpendicular if their dot product is zero, and the dot product to zero is just zero. And so it's funny because the zero vector falls into the kernel space and the space perpendicular to the kernel space. But yeah, that's an aside. Anyways, we've just shown that our theta zero, our initial parameter weights of our model, falls into the perpendicular kernel, like the space perpendicular to the kernel space. The kernel space being all the vectors that get mapped to zero. And so now let's start with our induction step. Which is, given theta k falls into the space perpendicular to the kernel space, we want to show theta k plus 1 also falls into the perpendicular kernel space. And I don't know if perpendicular kernel space is the right way to describe this, but just think of the perpendicular kernel space as the subspace that is perpendicular to the kernel space, in your imagination, I guess. Okay, and so we know that theta k we assume that this is in the space perpendicular to the kernel space, and we want to show that theta k plus 1 is in the space perpendicular to the kernel space. So if we can show that this equation, this loss gradient basically, or aka this part, is also in the space perpendicular to the kernel space, because vector addition, like if you add two vectors in the same subspace, they end up, like the result is also in that subspace for closed addition and closed. For closed addition basically. And that's one of the three properties we learned in Math 54 in like the first few chapters. And so if you kind of forgot, it's totally chill. But yeah, essentially if we can show that this falls into the space perpendicular to the kernel space, and we already assume that this falls into the space perpendicular to the kernel space, which is like kernel space perpendicular, then we can show that theta k plus 1 also falls into the space perpendicular to the kernel space. And so let's do that, right? So let's show that this falls into the space perpendicular to the kernel space. So if we calculate the dot product of our gradient right over here, I'm going to remove the constants because it doesn't really matter in the dot product for the purposes of our solving, and you'll see why in a bit. So like if I just write x transpose y minus x theta k, and I dot product it, this is, by the way, a dot product b, a comma b is also the dot product. It's just different notation from pre-calc, if you remember. But if I take the dot product of these with z, recall from problem A, being in our kernel space, if we can have it such that, and also z is not equal to 0. If we can have it such that this dot product is equal to 0, so if a dot product equals to 0, then a is perpendicular to b. And so if we can show that these two dot product together is perpendicular to, or is equal to 0, then these must be perpendicular to each other. And if z falls into the kernel space, then this guy must fall into the space perpendicular to the kernel space. And so if we actually do this, you'll see this whole thing is equal to a transpose b, which in this case is this transpose that, which is y minus x theta k transpose x. And remember, when we take the transpose, right, we basically switch the orderings. and we transpose both. And so the transpose of this is just that the transpose x transpose transpose just gives us x itself. So when we do that, we essentially get this new equation times z, or z being equivalent to our b right over here. And recall that xz is equal to 0 because, again, z is a vector that gets mapped to 0 when you multiply by our feature vector. And so this whole thing is equal to 0, which means we've shown that basically this term, right, alpha, because the rest is just constant, right, negative alpha k lambda, or loss function, is in the perpendicular kernel space. Because again, this whole thing was equivalent to this, which just came from this equation. And since theta k we assume is in the space perpendicular to the kernel space, and this is now also, we've just shown that it's in the space perpendicular to the kernel space because the dot product of that with a vector in the kernel space itself is equal to 0. And this property shows that they're perpendicular. Then it must be that since vectors are closed under addition, like it must fall into the same subspace when you like add or subtract, then theta k plus 1 must also be in the space perpendicular to the kernel space. And so let me just write down what I yapped about here. Let's see, how do I write this? Since we've just shown that this guy is also in like the perpendicular kernel space, and since vectors in the same subspace are closed under addition, this is a Lin-Alge property. We've just shown that through the equation theta k plus 1 is equal to theta k minus alpha k gradient. This guy is assumed to be in the perpendicular kernel space. We've just shown this is the case, so this guy must also fall into it. Then theta k plus 1 must also be in the perpendicular kernel space. And you will then see that you can propagate this, right? Like we start with theta 0, then we go to theta 1, then we go to theta 2, then we go to theta 3. And no matter what, right, every update continues to stay in the space perpendicular to the kernel space. Therefore, our limit, right, because we're told that this algorithm converges, our limit, theta infinity, it must also fall into the perpendicular kernel space because we just continue doing these updates, and every time this update is done, it always stays in this perpendicular kernel space no matter what. Okay, and so we've just shown this, but what we really wanted to show in this entire question is we kind of wanted to show that in gradient descent, the limit is actually the minimum Euclidean norm. It's actually the vector with the smallest possible length when we minimize it and find the answer. And so now, using this result, because we know that this is true, right? We know that x infinity is a solution, and we've just shown that this falls into the perpendicular kernel space. Then we can show that every other possible solution, because again, in part A, we show that there are infinitely many solutions, right? And we just show that gradient descent in this algorithm, we actually reach our like theta infinity ends up being an answer that falls into the perpendicular kernel space. If we can then show that every other possible solution has a norm greater than this, then we've just proved what we want to prove. Okay, so now we know that in gradient descent, our theta infinity actually ends up staying in this perpendicular kernel space. We want to show that every other possible solution has greater norm than our gradient descent solution. And by greater norm, I mean greater Euclidean norm. Okay, and how do you do that? Let's again let theta prime be some other random solution such that x theta prime is equal to y. And we know this is true again because in part A we show that in our specific question when d is greater than n, there's infinitely many possible thetas that could be a valid solution. And so theta prime is one example. And because theta prime does not fall into the perpendicular kernel space, because if you think about it, like we just showed that our solution falls into the perpendicular kernel space. And so there are many other solutions, but all those other solutions, they exist and they're actually equal to theta prime, like theta infinity plus some z such that z is in the kernel space. Because like you can't, if you don't add this z, then or like this is not another possible solution, right? It's the same solution. Okay, so if we add this z, which is in our kernel space, this is still a valid solution. We literally just showed this in part A. And so let me actually write that explicitly. So theta prime is equal to theta infinity plus z, where z is in the kernel space. And this is because since theta infinity is in the space exactly perpendicular to the kernel space vectors, all other possible solutions must have some z added to it such that it's still a valid solution because z falls into the kernel space, so it doesn't really affect the final answer. And through this, we can say our new theta prime norm, it's equal to this gradient descent answer plus some z, where z is a vector in the kernel space. Remember again, from part A, adding that extra z doesn't change our answer. We can add infinitely many vectors in the kernel space to our solution vector and provides us another solution that's valid because x theta is still equal to y. And so doing that, when we solve for this norm, we get theta infinity plus z transpose theta infinity plus z. And this is equivalent to theta infinity squared plus 2 theta infinity transpose z plus z squared. We just multiplied it out. And note how our theta infinity, remember, it's in the perpendicular kernel space. That's how it was defined. Or like that's what we found just now, right? We just found that theta infinity is in the perpendicular kernel space. And since z is in the kernel space, this dot product, which is what this is, must be equal to 0. And so this means that this entire thing must be equal to 0. And so we're left with theta infinity squared plus z squared. And since z is not a 0 vector, right? Because our columns are linearly dependent, so like there are other solutions z that are not the 0 vector and still map to 0. And so therefore the norm of z must be greater than 0, which means that this equation is greater than that. And so we've literally just shown that our, oh, this should have theta prime, by the way, or any other solution other than the gradient descent solution ends up being greater than the gradient descent solution in terms of its norm. And so since this is the case, since this is the case, this is the case, that's the case. So we have theta prime is always greater than theta norm, or theta, I guess you can say theta prime squared is always greater than theta norm squared, which means that our theta infinity must have the minimum Euclidean norm. Therefore, theta infinity is a minimum norm solution. Okay, and that solves part B. So it was pretty long, but essentially the whole point of this was to basically say, when we have our theta infinity, which is found through gradient descent, and it satisfies this equation, it remains in this space, subspace perpendicular to the kernel space. The kernel space is the space where all the vectors that get mapped to 0, so it's in the space perpendicular to that, no matter what. Because through every iterative update, this theta infinity stays in this perpendicular kernel space, so the final converged value, the final answer we get, is also in the perpendicular kernel space. And no matter what other possible infinitely many solutions there are, their Euclidean norm, their magnitude, is always smaller than our vector's magnitude, because our vector is the one that's in the perpendicular, in the subspace perpendicular to the kernel space. And so the whole thing was just to say that there's so many solutions that gradient descent could have, but it really just always lands on one solution, aka the solution with the smallest possible length or magnitude, which is pretty cool. It's pretty cool. Okay, and now let's move on to part C, which is basically show that this theta infinity, it's equal to this specific equation. And so we know from part B or from part A and part B, we have one, that x, and I'm going to write this as C above. Okay, so we know that theta infinity is a solution, and we also know that theta infinity sits in the subspace perpendicular to the kernel space. And so we want to show that this is equivalent to this. And so I'm going to start by saying, for number 1, let's show that this is true, right? X theta infinity is equivalent to, if this was the case, then this must be able to be plugged in. So we can write x, which is this x right here, times x transpose x transpose negative 1y. So this is theta infinity and this is x. And that's just what we get from the problem here. And notice how we can kind of like group this, right? This lovely guy and this lovely guy. I mean, it's like A times A or A inverse. And A times A inverse is just identity matrix. So it basically disappears and we're left with Y. And so that holds. And number 2, we want to show that this guy is in the perpendicular kernel space. And so if we let Z, again, be our vector that's in the actual kernel space of our feature matrix, and when we take the dot product, we have X transpose X transpose negative 1y. So this whole thing is, again, just theta infinity as given in the problem. And we take the dot product with Z, and this gives us, again, this dot product is equivalent to this whole thing transpose, like A transpose B, right? So A dot product B is equal to A transpose B. And so similarly, when we take the transpose, we literally get the transpose of this guy is Y transpose X transpose negative 1 transpose X transpose, and then multiply by that, right? Because it's A transpose B and this is just B. So this gives us Z. Oh, I forgot something. Okay, this is X transpose transpose, right? Because we transpose this and then we transpose it again when we transpose the entire thing. So this whole thing is actually just equivalent to X. And again, we know that xz is 0 because z is in the kernel space. And the kernel space is defined as it maps any vector z to the 0 vector. And so this entire dot product is equal to 0. And so dot product is 0 and z is in the kernel space of x. So theta infinity, which is equal to our x transpose transpose negative 1y, must fall into the perpendicular kernel space. And so both criterias 1 and 2 are solved. And so we've just shown that theta infinity is actually indeed equivalent to this solution. And that solves part C. Okay. And so that was really, really long. And now the question is like, why the hell did we do all that, right? Like, what was the significance of all this? And so I want to hopefully kind of give you a few takeaways, which I think is pretty cool. And so our takeaways is first, our context is we're fitting a linear regression model where D is greater than N, right? And so N is the number of rows, D is the number of columns. We have a lot more features, which means we end up having a lot more parameters than we do have data points. As said here. And so in 1a, we show that there are technically infinitely many valid solutions theta that perfectly fit the data x theta equal to y. And the reason is because of over-parameterization. We can add any vector z from the kernel space, right? Any vector z from the kernel space, and the answer would still be valid. And so this linear regression model has infinitely many thetas that we could use to minimize the loss. Which leads us to part B. What's super cool about gradient descent? It's that even though there's infinitely many solutions, it doesn't just choose one random solution. It actually chooses a very specific solution. So if we start by initializing all our parameters to 0, the final converged solution, theta infinity, it ends up being the minimum Euclidean norm, aka the vector with the smallest possible length / magnitude. Because the gradient updates always make sure that every update theta k is always orthogonal to the kernel space. It's always in the subspace that's perpendicular to the kernel space. And so that's really cool, right? Gradient descent always ends up with kind of like the simplest solution, the solution with the vector with the smallest magnitude as the minimizing solution, or the parameters that minimize our loss. And in part 1C, we actually showed that in linear regression with the specific cases, we talked about the minimum Euclidean norm solution that we talked about in part B. It can actually be calculated directly with a closed form equation. So there's actually an equation after that. After running all this like gradient descent, like the minimized answer can also be kind of written as in closed form as this. Our theta infinity is equal to x transpose times x transpose inverse times y. And this part is actually called the Moore-Penrose pseudo inverse. So there's actually a name for this. Okay, and so that concludes all of problem 1 in discussion 7. Hopefully that showed you some pretty cool insights on gradient descent. And now we're going to move on to question 2, which is about ROC curves.